Okay, welcome to day 2 of binomial probability, and we're going to do a quick pop quiz. No problem, you've got this. So there's 5 questions, 4 possible answers for each one, A, B, C, and D, and I just want you to bubble in your answers. And you're right, you don't get to see a question. That makes it tough. But pause this and pick your answers for all 5. Okay, welcome back. So the answers choices were A, D, C, B, and A. We want you to write down how many you got correct. All right. So now let's start going over this. The first thing I want to know is, was this a binomial setting? So to do that, we have to check our bins. B-I-N-S. Those are the 4 things we check every time we're checking for binomial settings. B is success versus failure. There can only be 2 outcomes, success or failure, and we have that. So even though there's 4 answer choices, each guess was either correct or it was wrong. Independence is the next thing. Is each answer independent of the previous one? Or in other words, do any of the trials affect each other? And they don't. Whatever you answered for 4 would have no impact on what you answer for 5. N stands for number of trials. There has to be a set number. And in this case, N equals 5, so we're good. And S is, do we have the same probability for every trial? And we do. A 1 in 4 chance, so the probability was 0.25. So we meet all 4 of our bins category. So it is a binomial setting. Once we know it's binomial, now I want to calculate the probability of getting exactly 2 correct. So I don't know about you. I only had 1 correct on mine, but that's okay. I want to see what is the probability of getting exactly 2 correct. So not 1, not 3, exactly 2. And we did this last time. So we're looking for the probability of x equals 2. That means I want exactly 2 successes. So I have 5 trials combined, and I want 2 successes. I have to multiply that by the probability of the success raised to the number of successes I want, so that's 2, multiplied by the probability of failure, so that's 1 minus p, raised to the power of the number of failures I want. So that's also equal to 5 minus 2. And you plug that in and we get 0.264. That's not too difficult to plug in, but there is a simpler way on our calculator. But if you use this, and I highly recommend you do use it, you do have to write this out, which means you write binomial PDF. And the P is important. It stands for a point, for an exact value. So the probability of getting exactly 2 correct. And we come, let me exit out of here. So when we come into the calculator, we're going to go second and then vars, which gives us a distribution menu. And we're going to arrow down to binomial PDF. Now notice there's a PDF and a CDF, so make sure you choose the right one. If you're on a TI-83 or an 84 with older software on it, you will just get this command with the parentheses. On this 84, it's going to give you the option. So number of trials was 5, the p-value is 0.25, and the x, the number of successes we want, is 2. I'm going to just hit enter, and then this is what it would look like on the older calculator or older software. Oops, I don't want that. I want to hit enter. And there we go. 0.264 is what it would round to. So again, binomial PDF, and we got that by second vars, which gave us the distribution menu. So that's the probability of having exactly 2 correct. Okay, we want to fill in this table of getting exactly X number correct. So I'm going to use the binomial PDF. The 5 will stay the same, the 0.25 will stay the same. And it's just this number that's going to change. It's going to go from 0, 1, 2. We've already done the 2, but let's plug these in. And again, I encourage you to go ahead and plug these in before just writing down my values, so you get some practice with entering that. So there is our probabilities. And of course, being a good probability model, these should all add up to 1. So now we want to find and interpret the mean of the distribution. So the mean is just like we've been doing, the sum of the individual x value times the probability of that x value. So 0 times 0.237 plus 1 times 0.396 plus 2 times that, etc. And when you add that all up, we got 1.25. Now be careful, this is the mean, it's not a probability, so it's okay that it's bigger than 1. And the way we would interpret that is after taking many, many quizzes, the average scored on the quiz will be 1.25 correct. Okay. Find and interpret the standard deviation of the distribution. So again, to do this, we've got to add our variances. So each individual x value minus the mean, we square that and multiply it by its probability, plus the next x value minus the mean squared times its probability value. And when we add those all together, we're going to get the standard deviation is 0.968. And of course, we want to interpret that. Ignore what's over here for now. And the way we would interpret that is that the number correct on the quiz of 5 questions typically will vary by 0.968 correct from the mean of 1.25 correct. Okay. Next, we want a slightly different variation. What is the probability of getting at most 3 correct? So at most 3 correct, that means I could have 0 correct, 1 correct, 2 correct, or 3 correct. So I'm just going to add my probability of getting 0 correct, 1, 2, and 3. At most means I include the 3. So I put those in, add them together, I've got 0.985. Again, there is a way we can do this on the calculator. This is called Binomial Cdf. The C is for cumulative. So we're going to have accumulation of 0, of everything up to and including the value you want. So we know how to go in here, second vars, and we come down to Binomial Cdf. Cdf. Number of trials is 5. Probability of success is still 0.25, and I want to have up to and including 3 correct. And we get 0.984. We're off a tiny bit if we do it via the calculator, but these values have been rounded also. So in the hundredths or thousandths place here, that's okay. We won't worry about that. What is the probability of getting 3 or more correct? So if I want 3 or more correct, so again, let's just look at these. 3 or more, so it's going to be the sum of those probabilities. So I could just add up, if I've made my probability model, 0.088 plus 0.015 plus 0.001, and I would get my probability. Or I could say, well, you know what, if I add these guys together and subtract the sum of these from 1, I would have these, because all of these together have to add up to 1. And even though it would be just as much work to add these 3 together as adding these 3, the calculator using Binomial Cdf will give me this value. So this is similar to with the normal distributions. When you wanted something to the right, you had to take 1 minus the probability of the cumulative distribution. So again, here I've added them together just using my probability table. And here I've shown you how to do it on the calculator. So the probability of success being 3 or more is 1 minus the binomial Cdf of 5.25, 2, because I want up to and including 2, and then I'm going to subtract that. Hopefully that made sense. Okay, let's turn this over and take a look at the back. Okay, so the 2 big ideas here. One is just repeating a little bit from last class is the bins idea. And the things that we want to worry about with bins: binary, independence, a set number of trials, and the same probability here. Okay, And if we have to describe a binomial distribution, the shape, we would have to make a histogram of it. So for instance, I could have used my probability table to make a histogram. To find the mean, we went over that. I'm going to show you another way to find the mean. Because it's binomial, we have a second way. And the variability, the measure of variability is our standard deviation. So with our binomial distribution, to find the mean, so we could do it the sum of all the x sub i's times p sub i's, but if it's binomial, there's a much shorter way. So to find the mean of a binomial distribution, we're going to take n, the number of trials, times p, the probability of success. And the way we would interpret that then is after many, many trials, the average number of successes, and you'd put that in context, whatever success is in the problem, is blank, mu sub x, out of the number of trials. So as a quick refresher, let's look back on the front here. You can see I had written this over at the side. So for binomial distribution, if I wanted the probability of success, I would take 5 times 0.25, which, wow, is 1.25. And again, we would interpret that as that after taking many 5-problem quizzes, the average number of successes or correct answers on the quiz is 1.25 out of 5 questions. Okay, the second part here, when we're describing our distributions, we need to know the standard deviation. And again, if we know it's a binomial distribution, we have a little shortcut here. Instead of having to sum up all those individual x's minus the mean, square that, multiply by the probability, we can simply take the square root of n, so that's your number of trials, multiplied by p, the probability of success, times 1 minus p, so your probability of failure. And the way we'd read that is the number of successes, the number of correct questions, typically varies by, whatever the value you get, from the mean of 1.25 out of 5 questions. So again, this is a much easier formula to find the standard deviation, but we can only use this if we've already shown that our setting is a binomial setting. Okay, so n is the number of trials times the probability of success times the probability of failure. So let's take a look at this check your understanding. I encourage you again to pause this and go through it. But I will go through now the answers here. So is it binomial? Absolutely. Success is going to be defined as you select a crinkled paper. Failure would be selecting paper that's not crinkled. Is it independent? Absolutely. Because each drawing does not affect the next. You put the paper back in. Okay, so that was important. The slip was returned to the box and mixed well. So that way it does not affect the probability and each trial is independent. N was 10 and the probability of success here was 0.25 because she put 25 of the crinkled ones out of 100. So yes, it's a binomial setting. And my histogram, we've got 0, 1, 2, 3, up to 9. That's kind of what it looks like. And again, we could calculate for each value here using our Binomial Cdf to find the actual value for each one. To calculate the mean, because this is binomial, I can say the mean of y, because we labeled this as y. Oops, you can't see that. Y is the number of times that crinkled paper was selected, is n times the probability. So there was 10 trials times the probability of 0.25 gives us 2.5 as the mean. And again, the way we would write that or interpret it is after many sets of 10 drawings, the average number of crinkled papers drawn is 2.5. And on the histogram, notice we label that's probability. These values on the x-axis are the number of successes. So right here at 5, that means that we had 5 successes, or we selected 5 wrinkled papers out of the 10. Sorry, that's messy looking. The standard deviation and interpret it. Again, because we've shown it's binomial, I can use this standard deviation formula. So n, the number of trials, times p, the probability of success, times 1 minus p, or in other words, the probability of failure. So nice quick formula. We multiply those three things together and take the square root, and we have 1.369. And the interpretation of any standard deviation follows this format. The number of crinkled paper selected in a set of 10 drawings typically varies by 1.369 from the mean of 2.5. Okay, let's go on and watch the second video.